give it a moment for Twitch. Let's see what we got. I am live. Do I see myself? I do. Twitch, you may be SOL today. The computer that I normally use to pull up your chat is not. See, if it's not one technical thing, it's another. Is not functioning, so you will get to live on my phone today. Historically, my phone doesn't show anything in chat whatsoever, so we'll see what happens. Okay, I'm pretty sure today is October 1st, 2024. In CSE466, we are done with ROP. We're now talking about dynamic, I think it's entitled dynamic allocator exploitation or misuse. So I managed to mess up 2 of the 3 words, but you know, we're going to the same place. It's heap exploitation. It's one of 2 heap modules. As always, we'll start off with memes here. This I don't think was any of you guys, but it's a decent dig. Or on Sunday, which is 365's deadline day, the memes channel gets flooded with a whole bunch of nonsense, and it becomes a actual task to complete meme reviews. So if you did post a meme and you think it was not garbage, and I didn't like it, I've also asked the TAs to, giving them the powers to like memes. If you somehow posted one and you thought it was amazing and we've skipped it, ping me in off topic, ping the TAs, ping someone, get somebody to look at it because it could have got lost in the noise. So we finished up ROP. Now, ROP, I think, was a pretty good module. Do you guys enjoy ROP? Okay. Did anyone enjoy ROP? All right, I got 1 thumbs up. A couple of thumbs up, and mostly just kind of like, yeah, all right. What's that? Except stack pivoting. So stack pivoting, I would blame class with the demo, but I think I made it up to you guys, so I don't feel responsible there. Stack pivoting is a tough thing to demo, and then one of the other things that occurred, which is on this meme slide deck here, is someone, and this happens in every module with some subset of challenges, right? There's some enterprising student who's like, all right, it says do a stack pivot, but you know what I'm going to do instead? I'm going to find this other thing that does something completely unrelated, and I'm going to tell everyone to do that. And then it becomes like this kind of mystery thing as far as what did the students actually do. So one of the things that I know some students were pushing and doing and just encouraging and whatever, it's still ROP, kind of, is there was a jump RBP gadget. And so some people were taking advantage of that to pull things off. When the correct answer is, of course, to use, well, not even that. This is what you'll commonly find. This is everywhere, right? A leave ret. If somehow you had pop RSP ret, obviously that's super easy. But a lot of people did this, which I would argue is not even ROP. It's something called JOP, which at the beginning of the ROP module, I said, hey, I might add challenges, and then I just didn't because I ran out of time. One of the things that I would have added conceptually would have been JOP. JOP works very similar to ROP, except instead of these gadgets being do something and then ret, where you're popping things off of the stack that determine where you go, with JOP, you have indirect jump gadgets. So you jump somewhere that then ret. So imagine we had something that could set RBP. You could set RBP and then ret to here to then jump somewhere else to ret to go back. And so you can start incorporating way more jumps instead of rets. And so it becomes JOP, jump-oriented programming, instead of ROP, return-oriented programming. Cool concept. I just didn't have time to hit you guys with it. It was one of the things I wanted to try and add this year. Level 13, 14, 15 were popular levels to dunk on or talk about here. Because the meaning of a stack smash, in some cases it was a good thing, and in some cases you could use it, or in some cases most cases it's a bad thing, right? Like something exploded. But there are cases where you can use that fact to your advantage. And so I thought these were cool challenges, good memes, if you got that far and tackled these challenges. But at the end of the day, I think ROP, I said it, and there's another meme that harkens back to this statement. ROP is a pretty simple concept at face value once you've done it a few times. There's a lot of ways to like blow your legs off and do things wrong, right? Oh, I put the wrong gadget, I didn't get the right base address, I am trusting the help text from the challenges. Right? There's a lot of things that, okay, you have to go through the pain of making a mistake and learning from the mistake, but ROP itself is actually pretty simple. You put a bunch of gadgets on the stack, and then you pop them off the stack and you go there, right? Hopefully, that's how you kind of feel about ROP now that we're on the other side of it. I don't want to say ROP. So ROP is not necessarily for this class, although I'll try and change that. But ROP is like instrumental to almost all modern exploitation. Everything turns into something and then you ROP. And then something and then you ROP. And so hopefully you feel it just becomes like bog standard. Where we are right now, depending upon if you started or not, that's totally fine if you haven't. We have, I think, 2 weeks to go through this, is manipulating something called the T-cache. The T-cache is the first layer of the heap. In this entire module, we're not going to go any deeper than T-cache. If you start Googling random things online and you see bins and large bins and small bins, and then we fill the T-cache and we unload the T-cache, and then there's pointers and there's double pointers and we have to fix, and you've gone too far. All right? There's a whole other module that covers how those things work. If you start going deeper down the rabbit hole, you are not approaching the intended solution, and you're going into a lot more complex things than what we need to for this module. So everything in this module is related to the T-cache, which is this first layer of the heap. And the T-cache is a great thing to start learning about when you're thinking about how does the heap work, or how does dynamic memory work, because it's actually pretty dumb as far as its implementation. And so depending upon if you started on it or not, but there are easy ways to trick the T-cache into thinking things that don't make sense. One of the things the T-cache does is you call malloc, and it gives you some region of memory. You're like, I need, I don't know, 20 bytes. And malloc says, okay, here you go. The first place that it asks to find this data is the T-cache. And if you mess up the T-cache, you can get it thinking all sorts of stupid things. For instance, this meme here is, I have, the T-cache thinks there's two regions of memory that it can give, and they're both the same thing. In a normal operation of a heap, that shouldn't happen. And so the T-cache is blind to a lot of these corruption things that you can do that we'll hopefully get to play around with here in the demo. I mentioned this, I think, on Thursday. This heap module has a pretty easy ramp as far as the earlier challenges. So the first, I think, 2 or 3 videos are Jan talking, and then I believe it's level 16. There's a 4th video, which has a much younger and better looking version of me that talks about safe linking. And safe linking is a modern protection mechanism. These levels of 16 through 20 are almost copy and paste, not exactly, but almost copy and paste challenges that you saw earlier. I don't remember which ones. So hypothetically, it would be 11, 12, 13, 14, right? It's going to be those challenges, except I'm going to copy them over and rename them as 16 through 20, and then I'm going to enable this safe linking thing. And the reason that I did that is safe linking as a mitigation strategy will materially change how you have to approach these challenges, even though it's the same scenario. Your exploit will become more complicated, and in some ways, the actual mechanism that you're exploiting will in fact be different. And so this is a great meme. Somebody I saw powered through this whole thing, which is impressive. I assume they were sandbagging, right? They had all of this and they just waited until it launched to bang it out. Submit all the flags. But historically, level 16 is just like a brick wall for students. So just know that going into it, if it starts off pretty easy. That's just more griping about safe linking. We aren't far enough as a class to get that one. Discord usage. So one of the things I noticed about ROP, at least with the launch of the ROP modules, people were working through it. There was a lot more active Discord discussion amongst all of you. You're creating threads, which is awesome, and you're talking about the challenges. That is, in fact, the goal, right? We didn't see that earlier. I was a little bit worried about it, but I didn't, didn't bring out the stick and be like, you must post 5 things, because that's really lame. So I'm glad to see that you guys are actually using it. One thing that I would try and stress is please do not create threads that are just entitled like level 8, because that really just does not make me happy. It is better to describe the concept that you're stuck on. And then one of the things that somebody on the Discord mentioned that I agree with is when you are describing your problem, it helps if you describe the problem statement, right? What does the challenge give you? Because if I'm looking at it, or anyone is looking at your request for help in your description, and you're just like, level 8, it does this. Well, you've now put that workload on the helper to go find the challenge, like go look at their solution, go run the challenge themselves, understand what's going on. And at the end of the day, these are the people that solve their homework because they know what's going on. So hopefully they have better things to do with their time. Maybe they're farming for extra credit, but help the helpers help you. And posting low effort things like level X, hey, this doesn't work, isn't a path to success. One of the things I am doing, which is like halfway done for silly technical reasons, I am locking all old threads. This isn't specific to this class. I'm doing it across the entire pwn.college Discord. I may not be able to delete all of them. I mean, I can, but I don't have enough buy-in to do that. Otherwise, I would. But what I can do is I can lock all of the old threads so that you don't respond to them, and someone from 6 months ago who was like, hey, I was stuck this. People will necro post and reply to the original author, the original question. Oh, I'm stuck on the same thing. What do you think? That pings some random person from 6 months ago, which is just rude. All right? I've tried to encourage people to not do that, but I've learned that's a futile effort. So instead, I'm just going to lock everything. And I'm going to do this automated. I'm going to keep things for maybe 2 weeks. 2 weeks from creation. After that, they get locked. So that way, these people that do help don't have to get harassed again in the future. And you'll not know it, but silently, unknowingly appreciate it a year from now when the next class is going through this material, because then they won't be pinging you like you are pinging the people who went through this before you. Yes. Help. Be good. Happy smiley SpongeBob. All right, Twitch, I do get to see something. What if we put context next to the level number? Like level X trying to XYZ. So I'm okay with this is my personal opinion, right? I'm not saying I'm going to hard delete things that say level X. If I get annoyed to enough degree, I will, but that's just more work for me as a mod. If you provide context to it, I'm okay with it. As long as it's not level 3, it doesn't work, right? That isn't context. It doesn't add anything. So it depends on what you're doing. Try and use your best judgment. I will probably throw some snarky comments at people who inevitably just post level X over the next week, and we'll go from there. But yeah, try and provide some context. One of the problems with having just level 3 is you post your problem, and then somebody else who has a completely different problem just says, oh, level 3. And then they just pile on. And so the thread goes, here's something, here's somebody resolving it, here's somebody else with another problem. Or they start interleaving. And that just becomes pain for everyone involved. And so that's what I'm trying to avoid. It's not an angry thing. It's just hey, we can do better. We aren't as bad as 365. Part of that is just because of volume. But I saw or heard 365 had a single thread entitled level 14 that had 500 or 600 posts. Most of which were, I'm stuck, me too. All right. So we're doing better than that. But I believe we can still improve, right? Constant improvement. All right, grades. So let's see, which one is this? This would be the solve distribution for raw. Looks pretty similar to what we had in reverse engineering, except the side that was over here is gone over here, right? So that's a good thing. This is a fantastic distribution as far as I'm concerned. Does anyone disagree? Like, that's a pretty happy looking distribution for people that are solving things. All right, solve rate. How did we solve things? One thing to keep in mind is this does start on Friday as far as the date that I picked. So I don't care if people start in the first 3 days. You could be wrapping up the prior module. So that's, what do we got? 2 days, 3 days, boom. What do we got? That's going to be Monday. We got people starting right there on Monday, and then people starting off in this first week. And we do pretty well. And then if we look at the kind of lower solve rates, and we look at these and chase back, they all tend to fall to locations that are people who started the module late. Again, reinforcing that start early. I don't know how many times we can reiterate that. Yes.
How is it that sometimes starts from 15 and 25?
Question is, can some people start at 15 or 25 or like some high number? So this is one of the things that people routinely ask about, just in pwn College in general, and how we deal with it as a website in ASU. So I launched the route module. There is a route module here under Bluebell, right? And so I've only solved level 1. I know nothing about route. People could have, and this is what these people did, is they solved these challenges betting that I would just throw the same assignment at you, right? If you solve it and ahead of time, and I happen to assign it, you get credit. If you solve it and I don't assign it, well, maybe you learn something, but now you have new work to do. That's the general rule of how we kind of approach this. And this is true across most of pwn College. It's always up to the instructor. So the instructor, somebody else teaches it, they can make up whatever rules they want, right? So like what I say doesn't bind any other instructor. But as a general rule of thumb, that is what we've kind of agreed upon in the core pwn College classes as far as how we handle this scenario. So for instance, right now you were assigned dynamic allocator misuse. I'm gonna tell you right now, it's this exact same thing.
But this has no chat.
Does it? I don't think it does. Everyone else doesn't think it does. So it depends on what I do. And it's my choice running the course. Like, do I want to include some of them? Do I want to include all of them? Do I want to include none of them and give you new challenges? It's whatever I decide. That's why I have this concept of launching the challenge on Fridays. Like from this point going forward, it'll always be a Friday. That is when you know what is being assigned to you as a student in the class. There are people who will work ahead, and I will not tell you like what I'm doing. I know what I'm doing. But you have no guarantee, right? So a good example of this is in 365. They launched a crypto module. This crypto module has 31 challenges. But I want to say the entire back 15 are brand new. They just added them to it. So if somebody had solved all of their crypto stuff that was on the orange belt, anything that they reused, they got credit. So they started off at the beginning of the module assignment with stuff completed. But they still have to complete the new stuff that's assigned. Yes?
Is the new stuff that's assigned in the class, will it become part of the belt? Or?
So that is up to the instructor and like how they decided to add the material. The answer more than likely here is yes. And if we look here for cryptography, so this will include everything. You see where the solve cutoff drops? We have 3,000, almost 3,000, about 3,049. Because this I think is still past. Is this still past month or is this all time? If we go all time, it'll even be more brutal. Oh no, that's not going to change this. But you can see where they added the new challenges. And so it's up to them. As challenge creators, we can do either. So one of the things I said on this point with yellow belt, green belt is like the stuff that I'm doing here in the class is going to reflect on the belts. I was talking to somebody about whether I'm going to do that dynamically. I'm just going to wait until the end of the semester and then shift everything around at the end of this course. It makes the most sense because there's other things that need to line up. So we'll just have one big shift at the end of the semester here as far as what changes on the belt, aside from these type of things where they're expanding on content that already sits somewhere. Nothing else from Twitch. Okay. Yes.
Did someone just solve all the chapters in one day?
Where am I? We're looking here. Yeah. Is there a straight line?
Red line.
Oh yeah, that's a sandbagger. So one of the things that one can do, and so we could easily see who this is if you are aware of how. Do you know how our scoreboard works on the site? So one of the things, boom, we're here in software exploitation. We go to, I don't want to be there. I want to be in 494 or 466. My bad. 466. And then we go to dynamic allocator misuse. We go down here. The default scoreboard is for the month. It's not as bold as it could be. But by default, it solves within the month. And when we launch it from a class, it only solves after that launch date. So what happened here, right, like you still get credit for the grade, but as far as the scoreboard, if this person, which is clearly this person, if Z function here worked ahead, but they really wanted to be rank 1 on the scoreboard, the optimal game theory play would be to solve everything, submit 0 flags, bet that I'm going to do the same thing. So then when it launches, they have all of the flags, and it's after it launched, and so they already have all the flags, and so literally all they did was they copied the flags that they already had from the solves on one day, hence the straight line. It's part of the reason why, one of the things I really like about when I took pwn.college is the fact that the instructor would like make a big deal about the scoreboards and the ranks. I wish I could, but because I know students will gamify the way that we do things, I don't. Because this doesn't mean that Z function was like the fastest at solving this stuff, right? I mean, they could have spent the past year working on this module, then they just saved all the flags for this moment. Well, that doesn't mean anything to me, right? All right, it's cool. They're rank 1 here. Now, if I have a module that is all new, or I extremely heavily modify, so it's impossible for someone to do that, then I'll make a big deal about the rank. I'll bust out some like pwn.college challenge coins, and I'll be like the top 5 people to solve everything. We'll get one of these. We'll have some fun with it. But as long as I know, which I've always known, and you just happen to identify from this line right here, people can game the system. I don't think that's a fair competition for those that are waiting for stuff to launch. Great question, though. Didn't realize until this week that flayed hoarding meta was applicable to pwn.college with respect to challenge coins. So we don't have a hard rule on challenge coins, but I'll say that I try and be very fair about how I do things. I may be harsh, but I try and be fair. And so to me, I'm not going to reward someone for doing that. My personal take. Cool, if you're the first one, right on. Here you go, right? But it's got to be something fresh so that everyone is competing on fair ground, right? That's kind of the way I see it, or pretty close to fair ground. Otherwise, I'm actively encouraging this type of behavior, which it's known to happen in war games and CTFs, but it certainly isn't what I want to try and encourage, right? Because I really enjoy the spirit of competition. It's one of the things that made me work really hard on this course. And right now, we have that to a degree. I was rank 1 in everything when I took the course. So where are we right now? This is course grade, again, excluding extra credit. Right, at this point, it's a meme. The extra credit will get there soon, TM. Course grade, I didn't calculate the average, but I don't think the average is going to be a horrible grade. If someone wants to math it from that slide, have at it. This is pre-extra credit, so I imagine the course average has to be, just looking at that graph, like 85, like a high B. And then you throw in extra credit, like we're cruising. All right, Dynamic Allocator Misuse is what we launched on Friday. It is running for 2 weeks. Checkpoints on Monday to do the following Monday after that. Hopefully this pattern now exists. We have a nice pattern and schedule to this stuff. Logistical things. Fall break. So I'm saying this now, and I'll probably say this again, but fall break is the 12th to the 15th. This does overlap with the tail end of Dynamic Allocator Misuse to do that weekend. So if you have big plans for fall break, please plan accordingly. This also overlaps with the launch of Program Exploitation, because it's going to launch that Friday before. They're still going to launch as scheduled. Yes, that means I'm that mean guy that's assigning you stuff over fall break. I'm sorry, I try not to do that if you look at prior courses, but the content that we want to try and cover here necessitated it. The nice thing here is it's not like in the middle of it. Just don't procrastinate on the heap one. Demo plans. So does anyone have anything from Rob that was just like, oh my God, we need to clear this up? No. All right. See, Rob was easy. All right. Rob was an easy module. You could easily do it in a week. I think Rob is easier than heap. I know some people, probably Z function, right? Who just sandbagged it and now just wants to troll you guys and say everything's easy. Some people are expressing that they think heap is easier. The reason that I say ROP is easier is because you're reapplying these same concepts you already have, right? We're doing some type of buffer overflow. We're doing some type of memory corruption. We're messing around with that return address. It's stuff you've already done. Now, heap exploitation is still memory corruption. It's still memory corruption of pointers. But what these pointers are and how they relate to each other is going to be very different than what you've done so far. And so that is why I say heap is harder. It's just there's a lot more newer concepts that you have to pick up in order to work with the material. Route 10 was like a 2-gadget level, wasn't it? I don't know. I'm doing it from memory. I don't know the levels. All right. How many people here have like looked at the heap videos? All right, we got a minority. That's fair. Like it's, you know, it's first class. So it's let's see what we got here. So some of this for those watching, what do I got here? Rob was best Rob. Okay. Did I miss something? Did I just talk about Rob too much? I like Rob. Rob. I didn't realize that I was being graced with the Adam Dupay. All right, so we're gonna launch here level 1 of the assignment. I didn't have time to throw together a play binary, and honestly, the challenge binaries do a great job of showing you kind of debug information to think about how the heap works. Let's look at Tcache stuff. Yeah, we're getting there. Carrying me through 340. Okay, yeah, Adam's a pretty cool guy. All right, so if I run this challenge, and this is pretty common to like heap exploitation binaries or challenges in general, you're provided some type of menu of actions. Does everyone know what malloc is? I got a head wave. All right, who does know what malloc does? Wants to say? People, yes?
It allocates memory. You ask to allocate some bytes.
Okay, so the statement was it allocates memory. Well, what is allocating memory? It gives me a pointer to some blob of memory. Why would I need that when I have the stack?
It reserves some memory and gives it to you so that we can play with large amounts of memory.
So it lets me play with large amount of memory, but I could make a really large region of memory on the stack, couldn't I? Like, there's nothing stopping me from just like having the world's biggest function frame. It's just like 1 gigabyte in size. I mean, maybe something's stopping me, but in theory.
But it's not dynamic. Heap memory is dynamic. It changes at runtime.
Okay, so the stack changes at runtime. The stack is for local variables. And so when that function returns, I lose that space. We're gonna try the drawing right now. All right, this is where it all goes off the rails. Boom, boom. Does technology work? Yes. All right, I had to wait for the Twitch delay. Okay, so if I have, that's text. There we go. If I have my stack, it's some region of memory like this. It's going to grow down. This is where main is. Main's going to call challenge. There's a function frame here. I could have some variable here inside of challenge, right? But when challenge returns, I lose access to this variable. Because the stack frame returns, this now goes away, and I can't rely on that value that was stored on the stack. So if there's some value that I need to be long-lived, I need it to persist across many function frames. There's two things that I can do. Yes, so one of the comments here from Twitch is it's better if it's supposed to last longer and will last across functions. There's two things that I could do, and this is like a general programming idea here, that if I had something that was long-lived, I either declare it way up here, because there's nothing that stops me from having a variable up in main, and then challenge, which can call func1, which can then call func2. All the way down here in func2, I can still reference that variable that's up in main, right? I'd have to like pass a reference down to it and make sure that func2 has that address, but I could do that, right? However, that would be pretty lame. So if I need to get a region of memory and I don't know how big it is, this is something dynamic. The stack is static. I have to know at compile time how big is a function frame going to be. And this is where the heap or dynamic memory comes into play. The way that the heap works is there is, and we're only going to talk about Tcache, there's some blob of memory called the heap. I'd pull it up in GDB, but the way I'm doing this now makes hopping kind of lame. Then I have my stack. Now, when I call malloc, right, in my code section here, something is going to call malloc. And it's going to say, I want something that's, I don't know, 20, hex 20. That's a beautiful hex 20. It's going to call malloc hex 20, and it's going to store it somewhere. We're going to store it on the stack. So A equals malloc hex 20. What happens is some region of memory inside of the heap that is hex 20 in size is returned, and we get that as A. So then A equals OX, I'm going to call it heap, right? It's some pointer into the heap's region of memory. That's what malloc does. Any questions about malloc? Okay. Free is the reverse operation. Free says, hey, I'm done with this pointer, right? There is this block of memory, and I was using it, right? I said A equals Rob. We put Rob over here. And then when we call our code, calls free, and we call free on A. We are telling the heap, I am done with this region of memory that is A, and I will never access this memory address again. That lets the heap know in its internal tracking of state that this is all now something that we can work with again. So this is like a super high-level reasoning about it. But that's the purpose of dynamic memory or the heap. Now, when I called free here, I said that I'm telling the heap, you don't get to see it now. I'm telling the heap that I'm never going to use this A variable again. Does that mean that I have to? Yeah. So in this challenge, I can malloc, I can free, I can put, I can read the flag, I can quit. All right. If I malloc, it says, how big do you want to malloc? In my demo or my scribble here, I was mallocing hex 20, so that's 32 bytes. Let's do that. Okay. The value of malloc is now stored in this array of allocations. Allocation 0 has this address. This is a pointer into that heap region of memory. Now what happens if I free? Well, we've now freed that pointer. And the challenge is going to print out the state of this T cache. And this is the thing that we're going to be working with this entire time, through this entire module. Because I said that we can malloc and we can free, and it's great to say I free and I just tell the heap, hey, I'm never going to use this again. But imagine that I am mallocing many things and then I'm arbitrarily freeing things. The heap has to keep track of all of these. And the way that it does it in the T cache is with a simple linked list, a singly linked list. We took data structures, we know what a linked list is. Kind of, sort of, hand wavy. All right. This is a cache in the literal sense. So this is a bin that is a list of things that have been freed that are of the size 25 bytes to 40 bytes. There's a series of buckets. They call them bins, but it's not, get that confused. So when I malloc and free something of size 32, there is a bin for things of size 25 to 40. The T cache is how we're tracking all of these things that we freed. And so I malloc something, I said I'm done with it. The T cache says, all right, cool. Here's this thing that I got. It's in this size range. And the next thing is null. So if I ask for something of 32 bytes again, the T cache is a cache layer. It's an performance optimization. It's going to look at this list and be like, do I already have something that meets that need? So if I malloc free and then malloc again, we see that I get back the exact same pointer. I malloced it, it gave it to me. I freed it, it was like, cool, we're going to store it in this list in case you ask for it again. And then when I asked for it again, it gave me back the exact same region of memory. This is what the T cache does. Now, I said it's a singly linked list. This is not going, this level won't let me do what I want to do. Let me go to a later level. Okay, so this one is same idea. I have malloc free, puts free flag, but it lets me perform multiple mallocs, so I can hang on to multiple pointers. So in index 0, I want something of size 32. In index 1, I want something of size 32. In index 2, I want something of size 32. So now I've asked and received 3 different pointers. I'm now going to free all 3 of them. So we're going to free, let's do it backwards. 2, we're going to free 1, we're going to free 0. Now this T cache now looks a little bit different. That's why I had to choose this challenge, or a later challenge, because this allows us to build this. And I said that the help text is actually pretty solid at showing us what's going on here. So the T cache is a singly linked list. So there's a head of the list, which is going to be this location right here. This is the last thing that I freed. I freed index 0. And if we go back up here, 72C0, which is what I freed here, is at the head of the list. A singly linked list works like a stack, right? What is that? Last in, first out. So the last thing I put in is the first thing that's going to come out. Now, a singly linked list means that we have a single next pointer. If we look through this thing, this has some metadata, which if you watch the videos, Jan will cover a little bit. The size is the size of the chunk. When I was drawing something, we just call it like this blob of memory. Well, there's two terms that matter when we're talking about the heap. There's the allocation size, which in this case was 32, which would have been hex 20. The size of this is actually hex 30. This one is a lie. This is the size of the chunk. The allocation is what users are supposed to interact with. I asked for hex 20 bytes. I can pretend that I have 20 bytes from this pointer to mess around with. The extra bytes in the size of the allocation is used to store metadata and for the heap to use to think about and organize how things work. That's why this size doesn't match what I asked for up above. I asked for hex 20. It actually created chunks of size hex 30. But from the user of the heap, I still only have hex 20 bytes to play with. So when we freed this, one of the things that happens is there is a next pointer. There's a singly linked list. The next pointer points to the next thing, the next free chunk of that size. And so we see here the next pointer points to 172F0. And if we look right here, that is the next chunk that would be used to satisfy an allocation. And we go from this location, the next pointer is 17320, which then points to the third allocation. The next pointer of the last thing is null, indicating the end of the list. Now there's a couple other values here. There's this previous size and there's size. This is other metadata that is used by the heap to verify what's going on. Now, this printout from the challenge is helpful and useful. It helps us understand what these values are, but I don't know that it does a good job of visualizing these chunks and regions of memory. So I'm going to draw these chunks. This is why drawing is awesome. And then we will take a look at how we can look at these with GDB to kind of look at these values and see where they actually exist in memory. Are people following along? Is it boring? Are we kind of so-so? We're seeing where it's going. Unsure. All right. Quiet crowd today, man. Quiet crowd. All right, we'll go back to pictures. Nice. Now, this is what's lame about this implementation is I can't get the literal addresses that I just showed you. I can't like jump rapidly back and forth. But what I did, if we were to try and do this, our order of operations was malloc, 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 free, free, free. Okay, and this was all the same size. What did I go with? 32, 32, 32. It's important that they're the same size. If they're different sizes, they're going to get stored in different bins on the T cache. Question?
But if the sizes are in the same range of the T cache, 20 to 45, they would be stored in the same.
Okay, the question for Twitch was as long as they're in the same range, and that's a more accurate statement, yes. So with the bins, there was that size range. It wouldn't literally need to be 32, but I would encourage you, just for your own sanity.
It's still be in the same linked list, right? If they're in the same range.
If they're in the same range, what happens is, like, if I were to say I wanted to allocate 31, it's going to round up and you're going to get the same chunk backing it, right? But from a user's perspective, the contract between Malik and the program is I can only use what I request. It would be really weird to request 31 bytes. Generally speaking, we do things as multiples of 8, but you could.
My question was, if I malloc 32 and 31, and
Yeah. Okay. So if I mallocked 32 and then I mallocked 31, and then I mallocked 26.
All of them go into the same list.
Once you free them, yes. Yeah. The important thing to keep in mind there is that they go into mallocing gives the program a pointer. I'm just going to use A, B, and C for these addresses, representing whatever it is I got here, and here, instead of writing literal values. Yes, but your statement, you're correct. They'd go in the same Tcache bin when they are freed. So I malloc A, B, and C. I then free. Let's do A, B, C. Okay. So these initial mallocs just come from the heap. There's nothing in the Tcache. We're going to assume nothing happened. What happens when I free A? All right, there's something over here. It's called the Tcache. The Tcache has a list of head pointers, right? So this is the head for, we'll say, size hex 20 or hex 10. We'll have a head pointer for hex 20. We'll have a head pointer for hex 30. When I free A, I'm saying I'm done with this allocation that was of size 32. So we're giving it back to the heap. The heap says, all right, this is small enough. It fits in this size right here. So head pointer now points to A. And we'll make A look like this. This is A, because A is an allocation. Now, when we had that printout by, can I zoom into this? Yes, I can. When I had that printout from the challenge, it had this previous size and all this nonsense going on as well. These exist in memory. And so a better way of thinking about this is A points to this spot right here, kind of in the middle or a little bit after the beginning of the chunk. And what we have here is prev size, next, and then this spot, this remaining space here is just unused space. So when we free something, the heap is going to write these values into that memory that we freed to track its internal state. Now, what should this next pointer be? Yes?
What are 0x10, 20, 30?
The question was, what is 0x 10, 20, 30? So I'm using this as a representation of the bin size. All right, if we were to look at the challenge, I was asking for allocations of size 32. This bin is for things of size 25 to 40 bytes. The chunk size is hex 30. So those are the different head pointers. So if we run the same challenge here, let's say I malloc into index 0, something of size 32. I malloc into index 1, something of size 32. I malloc into index 2, something of size 64. I then free 0, I free 1, I free 2. What we see here in our printout is these are not all pointing to each other. Right? There is bin tcache bin 1, which is this list right here. And it has the two chunks of size hex 30, where the last one is null, right? Now, when I freed the 64 byte allocation, that was too big. It was outside of this range. So that's going to go in a different list. And so here, when I say head or hex 30 head, it's literally this head pointer, right? There's a pointer to where is the first thing of the list, which is this right here. This is my 64 byte allocation, which would be hex 40. But we see the actual chunk size is hex 51. Yeah, because the chunk size will be larger than the allocation. It's not always plus 10, but we can kind of hand wave that for the time being. So there are different lists. And so what I'm trying to demonstrate with my artistic skills here is that there are multiple head lists. Right? One of them can point to null. This one can be null, right? Because the only thing I did so far is I freed one thing. I freed A, which was something of size 32. It was an allocation of size 32, which will end up with a hex 30 chunk. So when I freed something that was 32 bytes, it's going to actually be a hex 30 size chunk. The head pointer will point to where A is. What happens when I free B? What happens to my drawing here? This is a singly linked list that functions like a stack. Oh no, do I not have the ability? I do not. Gosh dang it, Apple. Okay. So the statement was that something points to B. What points to B? You think this points to B? So it doesn't, because it works like a stack. So think about if this was really, really, really long, right? There is a limit to this, but there's many nodes. Then when I free something, I have to traverse this whole list. And this sounds like whatever, you're dereferencing a pointer, right? It can't be that much work. But the heap is accessed all the time in large programs. We're constantly getting dynamic memory. We're constantly freeing stuff. So we actually care quite a bit about performance. And so it doesn't make sense to traverse this whole list every time that you do it. Instead, we push it to the front of the list. And so this becomes B, and then B's next is going to point to A. And it'll have a prev size, a size, and then a next. And this next will point to nothing. It's null. Anyone want to guess what happens when I free C? Right, C gets pushed onto the head. The rest of this shifts on down. So then we have a C. So I have a prev size, a next. This next is going to point up to B. This thing now points down to C. And so this is my singly linked list. There's one pointer, goes to the next thing, goes to the next thing, goes to the next thing. That is the Tcache in a nutshell, like normal operation. So from right here, what happens if I malloc something of size 32? How does that operation work? It's going to look at says, hey, I need a chunk of size hex30. We go to the head. We grab whatever the first thing is that's there, which is C. This guy is C. All right. We grab C. We pass C to the program, and then we just fix this pointer to point up to B. There's not really too many moving parts in normal operation, right? And this guy gets returned to the user. Malloc. I have horrible handwriting. That's why I studied computers. I can type. I can't draw. Right. Okay, so this is like the normal operation of this thing.
The B's next pointer is pointing to A. But
yes.
After the jump.
It would point to right here. If we wanted to be perfect. So one of the things that you'll notice I did with these next pointers is I'm not pointing to the beginning of the chunk. I'm pointing to the beginning of the allocation. This is something that I'm probably going to get pedantic about on the Discord. Because people feel like, oh, it's a chunk or allocate. Like, there's a difference. The chunk is the region of memory that the heap is entirely using. The allocation is the region of memory that is returnable or writable to the user. Now, in this drawing, I just kind of said, hey, these regions of memory are like these floating blobs of memory, right? There's just this A, and there's this B, and there's this C, and it's just there, right? But if we go back up to my drawing, my first one, where I had this blob, these could actually be right next to each other in memory. So if they're contiguous, like I'm going to call it physical. I don't have a good term here. Their physical proximity to each other is distinctly different than their relationship on this list of stuff. But one of the things we saw in the memory corruption module, and again in RAW, is the concept of memory corruption. If things are contiguously next to each other, like if I were to write A, we said we know here A is hex30 in size. What happens if I read into some pointer to A and I read in, I don't know, 90 bytes? I would overflow this region of A, I'd start messing up B, I'd keep going, I'd overflow and mess up C. And so when you're thinking about these chunks, there's two things that you have to be aware of in these allocations. What is their physical proximity to each other in memory? This has to do with the literal pointers that are being returned. Where are they next to each other? How far apart are they? And the second thing is the relationship of the metadata between them. And this module is going to take advantage of these two components in different ways. So the very first level, we'll circle back to my initial question, which was when I malloc and free something, I'm telling the heap I'm not going to use this pointer anymore. I malloc something, I free something, it's in the T cache. All right, I puts, there's nothing there. What does read flag do? So read flag is going to, this is a help level, it mallocs 741 bytes, it returns the pointer, and then it reads the flag into it. But am I going to get the flag now? No. So how do these things relate to each other? Well, free doesn't null that pointer. When I say free A, I'm telling the heap I'm done with A. It doesn't mean that I've set A to be 0. This is a very common mistake in languages where you have to manage memory or manage dynamic memory, is you fail to null a pointer. Then, if this A value is still pointing to that allocation, I could use it later. So I could use malloc, something of 32. I'll free it, and I'm going to call that puts command. What does, this is a bit messy. Where is my puts? Read puts. Oh, wait. Did the challenge actually show that for us already? So I don't have to? That would be amazing. It does. So when I run puts, I didn't see this. It is going to call puts, which is the equivalent of print, right? On the pointer to the allocation. Now, this challenge doesn't let me read anything into the allocation. The question is, does the challenge null that pointer? It frees it, but does that pointer still exist? I'll go down on this in IDA. Okay. We see if I pass in free, it will call free on the pointer. It does not set this pointer equal to 0. So this is a scenario where they didn't null out that pointer. This is a known type of vulnerability because this pointer is referenced in other locations, right? So I could malloc something, free it, and then print it after it's free. This is aptly called use after free. Because when we ran free on this pointer, we told the heap, you can use this memory for something else. I'm not going to use it again. And then it's my job as the user space program to make sure that I don't use it after I told the heap that. But clearly it's possible to do that here. Anyone have any ideas on how to solve this? Or how to take advantage of this? What do we got?
Once it frees it and the pointer isn't done, as we saw that when you ran the read flag command, that it is also getting some bytes to memory. You can potentially use that to have the flag in our elevation 0 and print that out.
Okay, so when I ran read flag, the challenge tells me it's going to malloc something, and then it tells me the address of it, and it reads the flag.
So we could potentially use that to point the flag towards the malloc that we do, and when
But it's not going to the malloc I did. This is the malloc I did.
yeah, but when you free it,
I did free it. That's why it's here.
it needs to be in the same range as well, right?
So it needs to be in the same range. And so I'm mallocing 32. So this goes back to those ranges in the bin size. Here, this Tcache bin is for things of size 25 to 40. When I do read flag, what size does it malloc? 741. Is that going to pull from this Tcache list? No, this is for small things. So how can I get around this? What do I got to do?
Maybe you can
Malloc 741. And then I read flag? No. That puts? No. What's going on here? Okay, I malloc 741.
Yeah, malloc.
Well, why do I need to free it? Well, what is my goal here? What am I doing?
We need to make the read flag use the read pointer.
I need to make
Read flag.
read flag use that pointer. So I need to get that pointer into the T cache. So that way when read flag asks for something of 741, it's going to pull it from the T cache because it's already there. So let's free. So I freed my 741 size there. And now I push this pointer to the T cache. Or not, yeah, whatever. I've pushed it onto that stack, on that singly linked list. It's at the head of the T cache. So now, if I call a read flag, it's gone, right? Tcache bin 45 had that big old boy that I freed. And then when read flag malloced, it pulled it from the Tcache because there was already something there that satisfied what read flag was asking for. And this has a use after free. So we took a look here in IDA. When it's freed, we don't null out this pointer. So that means when I puts, it's going to put on that same pointer, that same memory address that read flag was using. So read flag had a pointer to that location on the heap. And then I had one from when I got that memory address from the heap as well, which is why I could put that location, because I'm using that pointer within the program after it was freed. And so I told the heap I'm never going to use it again. So the heap was like, all right, cool, somebody else needs it. I'm going to give it to them. Give it to that function. But then I do use it afterwards, which is where that security concern is. It's unusual. I'm actually solving a challenge for you guys, but it's level 1, right? I think that's fair. So let's take a quick look at my GDB init. Twitch is quiet. Do I have Jeff? I do. So I'm going to run the old challenge here. We're going to malloc. Actually, I want to do something that lets me have multiple allocations. So we'll do 3. I'm not going to solve 3. We're just going to use it as our stand-in here for debugging. Okay. I malloc into index 0, something of size 32. I malloc into index 1, something of size 32. I malloc into index 2, something of size 64. We'll malloc into index 3. Apparently I want 54, size 32. I'm going to free in the same order, so we'll free 0, we'll free 1, we'll free 2. I think I had a 3. Yes, I did. Okay, so now I'm in GDB. The last thing I said I wanted to show was how to look at the heap. And this is where things might explode, but it's the last 5 minutes, so it's part of the course. If you have Jeff installed, there's 2 commands that are very useful. There's heap bins, which is showing me that same type of data is what the challenge help is. The challenge help, if we go up here, has this nice pretty table of where's the head pointer to this thing, where's the next pointer, here's the next thing. If we look at what Jeff is showing us, it's a bit more compressed, but we see that there's the Tcache bin size of hex 30. There's 3 things in it. Despite the arrows pointing from right to left, we actually read it from left to right. I don't know why. So this is the first allocation that'll be returned. It also tells us some metadata here about some of the flags on the chunk that we aren't going to touch on today. Here's our second chunk. And then here is our third chunk. Now I did another allocation of a different size. So we see here is the Tcache list for size hex 40. There's only one thing, because I wanted 64. I actually typed 54. We get hex 40, right? So it gave us a 64 byte chunk because I asked for something that was slightly smaller than that. It goes back to that weird number thing, right? 54 round up, we end up with a 64 byte chunk. And there's only one thing here. Do we see how those two relate to each other? We're showing the same information. One is just from the debugger, the other one's the help text. Obviously, well, not obviously, but the point zeros will have this nice, pretty printout stuff. The point ones will not. So that means that you will need to do some reversing, or you will need to utilize GDB to reason about what's going on. The other thing that you can get with Jeff, this showed me what is going on like with the metadata. Now there's other things in the heap here, these other bins. We do not have to concern ourselves with these things for this module. If you're interested, go check it out, but that's not what we're doing this week. The other thing that you are interested in when you're talking about dynamic memory, I said, is where are these chunks located next to each other? It's great. This chunk is at DA360. This next one is at DA2F0. Okay, so this first one is somewhere ahead of the second one, right? Just because the addresses are bigger than each other. We can look at these addresses and do some math and figure out where they are, and okay, maybe that's great. But if you're more of a visual person, you can do heap chunks. Now, pwn.debug has similar functionality, which I'll probably show on Thursday. Pwn.debug has a very good chunk visualization where it like draws ASCII things, and it's more artsy. But this is showing me where are these chunks contiguously in memory. What is the order of these chunks? So the first chunk is at DA010. The next chunk is at DA2A0. Then I have DA2C0, right? This is the order that I allocate. These are the chunks in contiguous memory. These are all going to be in order. And so this gives me an idea of what chunks are next to each other. So if I wanted to, for instance, do a buffer overflow, we're used to thinking about doing it on the stack. Overflows exist on the heap. I just have to pay attention to what chunk am I accessing? What pointer, which one of these chunks do I have a pointer to? What if it's this one? And I can read in, I don't know, hex 60 bytes. Well, this chunk is of size hex 30, which means there's 20 bytes from the pointer, because we are subtracting 10. So first hex 20 bytes would fill this allocation, and then whatever I wrote after that is going to start overflowing into this chunk here. That is what I have for time. Well, hopefully that's enough to get you started. Watch some videos. I do think the videos are useful. The challenges are pretty good at giving you demo help. So play around with it, and we will go from there. Thursday, I will have a actual demo binary instead of a challenge, which is just going to be very similar with a menu of malloc and free, and we're just going to mess around with all sorts of weird scenarios. All right, nothing from Twitch. All right, I'll leave you. Goodbye and good luck.